Now, we can start to construct something called a molecular orbital diagram. Dealing with hydrogen, we have two hydrogen atoms coming in. Each hydrogen atom has a single electron. So we have an electron there, have another hydrogen, another electron here. And they come together. And they can come together in a constructive fashion, where they're the same phase, like so. This is what is called a bonding interaction, sometimes called a sigma bonding interaction. Or they can come together in a destructive fashion, which is higher in energy. This is an anti-bonding interaction. And of course, atoms want to be the lowest energy possible, and so these two electrons join forces and come together in a bonding interaction. One has an arrow going down, one has an arrow going up. And this basically is the molecular orbital diagram of hydrogen. Now, there are essentially two ways of breaking a hydrogen molecule apart, or breaking a covalent bond. The first way of doing it is simply removing electrons from the bonding orbital. In fact, if you take hydrogen gas and you hit it with a cosmic ray, what you can get is H2 plus and a free electron. So essentially, what has happened here you have your sigma star orbital, which is empty, and you have your sigma orbital, which has 2 electrons on it. When the cosmic ray hits, it takes one of those electrons and ejects it completely from the molecule. As a result, you only have a single electron left in the bonding orbital. You have just weakened the bond between these two atoms. Normally, when you have the 2 electrons in the bonding orbital, the bond distance between them is 0.74 angstroms. But in this case, here you only have 1 electron in the bonding orbital. As a result, the nucleuses aren't as closely held together as possible. And the resulting bond distance between the 2 nuclei lengthens out to be 1.06 angstroms, which is still quite a bit less than the 2.4 angstroms of completely non-bonding, but it is significantly further apart than the case where you have a full bond between them. Now you only have a single electron holding these two together. If you get rid of that single electron and have no electrons whatsoever, the result is you have 2 H pluses, 2 protons near each other, and they are repulsed because now you have no electrons holding these 2 nucleuses close to one another, and the resulting positive charge here, repulses each other, and they go fly away. Now, that's one way of breaking a covalent bond, is removing electrons from the bonding orbital. Another way of breaking a covalent bond is adding electrons into an anti-bonding orbital. What I mean by that is, say you take hydrogen gas, which has 2 electrons in the bonding orbital, and no electrons in the antibonding orbital. And then, if you add 2 electrons to this, well, you'd like to go these 2 atoms to go into the lower energy bonding orbitals, but in molecular orbitals, you can only have 2 electrons per orbital. Here, this one's already filled, so the next 2 electrons have to go up above to the next available energy, and that happens to be the antibonding orbital. So when we add 2 electrons here, in addition to the 2 electrons here, now we have the same number of electrons in the bonding orbital as we do in the antibonding orbital. These electrons cancel each other out, and as a result, the 2 hydrogens split from each other, but in this case, one takes one set of electrons, another one takes the other set of electrons, and now you have 2 H minuses being repulsed by each other, and they go far apart. The way you add electrons into a system, well, one easy way of doing it is basically taking hydrogen and mixing it with an element that likes to give up 2 electrons, say sodium metal. Sodium likes to give up an electron, and you add 2 sodiums in there, and so when you mix hydrogen gas with 2 equivalents of sodium, you get 2 sodium hydrides, which are NaH minuses.